Here are the notes for Unit 2.4, the first and second laws of thermodynamics. We've been talking about heat and temperature, and energy can be transferred by heat, but for this to happen, we need a heat source. Often, a heat source is something simple like a candle or some kind of combustion. Energy can also be transferred by work. Remember that work is force times distance. And here are a couple of everyday examples of how energy can be transferred by work. If I rub my hands together and warm them up, what's happening is that the work that I'm doing from friction is actually turning into kinetic energy, and then it's turning into kinetic energy of the molecules that make up my skin. So remember that temperature is directly proportional to the average kinetic energy of the molecules that make up the substance. So in that case, the work that I do goes directly into heating up my hands. So you can try that for yourself. Another example that's kind of cool, if you have a rubber band around the house, if you stretch the rubber band very quickly and touch it to your lip, and you use your lip because it's more sensitive than the rest of your body, you should notice that quickly stretching the rubber band causes it to feel warmer. And again, what happens is that the work that you do on the rubber band, that work, energy is never created or destroyed, it changes form. So that work turns into an increase in internal energy of the molecules of the rubber band. And an increase in internal energy is a fancy way of saying the temperature goes up. You can do the reverse as well. If you stretch a rubber band slowly, and this is called isothermal, we'll use that word later, isothermal. If you do it slowly so that the temperature of the rubber band is allowed to stay approximately room temperature, and then quickly let it unstretch, you should notice that it feels cooler. And in this case, what's happening is the rubber band, when it's pulling your hands together, the rubber band is doing work on you before you do work on the rubber band. When the rubber band is doing work on you, it has to get that energy to do work from somewhere, and it gets energy from its internal energy. And when it gives up that internal energy, its temperature goes down. So another way to say this whole process is deforming a solid or changing the shape of a solid. Okay, so now we've seen that both heat and work can change the internal energy of a substance. And again, just a reminder, the internal energy is related directly to temperature. So I always want to have those two ideas linked in my head. As long as a substance does not change phase, the internal energy is proportional to the temperature. Okay, and we did have a formula, the change in kinetic energy. Actually, let me go back and look. I don't want to mess it up. Here we are. The change in internal energy, delta U, equals 3/2 nR delta T. There we go. And that delta U is equivalent to the kinetic energy of the substance. Oops. So there's the formula that I mean when I say proportional. Let's see. For example, pulling a nail out of wood involves work, which is proportional to the increase in internal energy of the nail. But in this next chapter, we're going to focus on work due to changing volume, and we're going to look at the specific example of gas in a cylinder. So we've looked at some examples of this already. We're going to have a cylinder, and the cylinder is going to have a piston, which I can push or pull and change the volume, the effective volume of the cylinder. Typically, we can measure pressure, volume, temperature, number of moles. And all of those things are related with the ideal gas law. The system is the substances of interest within a clearly defined boundary. The system is typically what's inside the cylinder. The environment is defined as everything outside and surrounding the system that can be affected or affected by it. So the surroundings are what's outside the cylinder. Now, we did some PhET simulations where we had a cylinder or a closed box, and then underneath that, there might be a fire. Okay, so that fire would be the surroundings. And then the gas inside the cylinder would be the system. Okay, consider gas in a cylinder with a piston. If work is done on the piston, then the gas is compressed. Now, again, we know that PV equals nRT, and basically this is an inverse equation. You may recall from algebra, xy equals a constant, then y equals k over x. That's a hyperbola. That hyperbolic shape is this curve here. Okay, I'm actually going to erase that because it's kind of ugly. Okay, we also know that work equals force times distance. And if I multiply that formula by area over area, what I can rearrange it to be is work equals force over area times distance times area, and that's equal to pressure times change in volume. So force over area, you may remember, is pressure. Let's think about this. If I do push down on a piston to change the volume, if that's my distance and this is my cross-sectional area, I know from geometry that the change in volume is going to equal that cross-sectional area times the distance. So that's just a little visual of how we get this. Now, we have to be a little bit careful here because as volume expands, when volume expands, that is the work being done by the cylinder or by the gas. And when the cylinder is compressed, that's work being done on the gas. And when the cylinder expands, when work is being done by the gas, we are going to define that as negative work because the gas is losing internal energy. When we do work on the gas, we're going to define that as positive work because the gas is going to gain internal energy. This is different than the way it's taught in AP Chemistry. So if you took AP Chemistry, this is reversed. What this also means is that we need to add something to our formula. Work equals negative P delta V. Because if you don't put the negative there, then these signs don't come out correctly. And again, in physics, we call work on the gas a positive value because it's going to lead to a change in internal energy that's positive. It's going to lead to a temperature increase. Let's look at an example. An engine cylinder has a cross-sectional area of, so let's do an example. An engine cylinder has a cross-sectional area of 0.1 meters squared. Let's sketch this as we go here. So I'm going to draw a cylinder. The cross-sectional area is 0.010 meters squared. How much work can be done by a gas? So by a gas means the gas is going to push and expand the cylinder. If the gas exerts a constant pressure, okay, now this is interesting. Constant pressure. How can the pressure stay constant? How can the pressure stay constant if this gas is expanding? Because normally, if the gas were expanding, the pressure would go down. So we're going to assume that N, the number of moles of gas, are staying the same in the cylinder. We're going to assume it's a closed cylinder. And R is a constant. We just found out that P, the pressure, is a constant. And we found out, let's see, the work is being done by the gas. So the volume is going up. This means the temperature must also be going up in this scenario. But the question isn't about that. I just wanted to make sure that I could make sense of what was happening here. The question is, how much work can be done by the gas? So again, for this work to happen, I'm going to have some kind of heat source. I like drawing in Notability so much I could waste too much time here. I have some kind of heat source that's going to be increasing my temperature. But that's going to allow the gas to do this work. That temperature is going to allow the gas to expand. And when the gas expands, it's going to push up on this cylinder and do work on the cylinder. Okay, so the big question is, how much work is it going to do? So the formula is work equals negative P times delta V. So we would have 7.5 times 10 to the fifth. And then my delta V, the change in volume is a positive value because the volume is getting bigger. So the change in volume is positive. And the amount of change in volume is going to be equal to the cross-sectional area times the distance. So that is 0.010 times the distance, which was 0.04. So I really just need to multiply this out. So that would be negative 300 joules. Now, we can say this two different ways. We can say the work is negative 300 joules, and this negative implies that it's by the gas. Or I can say 300 joules of work done by the gas. But I can't say both. I can't say negative 300 by the gas because that's like having a double negative. It's like I ain't got none. So we don't want to say both. We either want to say the work is negative 300 or we want to say 300 joules of work was done by the gas. Okay, so here it is. The first law of thermodynamics. The first law of thermodynamics is basically saying that energy is conserved. And what we're saying here is that the internal energy of a gas in this system is equal to the heat into or out of the system plus the work done on or by the system. And I've put the sign conventions here, and they are different from AP chemistry again. Q, when Q is positive, that indicates that heat is being added to the gas. When it's negative, when Q is negative, that's indicating that heat is being removed from the gas, or you also could say that heat is transferred out of the gas or it goes to the surroundings. Work. When work is done by the gas, when the gas expands, work is negative. And when work is done on the gas is compressed, the work is positive. Let's do an example. A total of 135 joules of work is done on a gaseous refrigerant as it undergoes compression. So one of the things we're going to learn about is that for a refrigerator to work, what happens, this again is coming later, but what happens is that there's a compressor, a cylinder, and the gas is compressed rapidly, and it's also expanded rapidly, and we do that to manage heat. We use that process to, I'll go through the steps later, but we use that process to pump heat out of the interior of the refrigerator. Okay, if the internal energy of the gas increases by 114 joules during the process, what is the total amount of energy transferred by heat? So to approach a problem like this, I'm going to use the first law of thermodynamics. The change in internal energy equals the heat plus the work. I'm going to identify my variables. I know that the work is 135 joules. I know that the change in internal energy is 114 joules. And really all I'm going to do is plug in and solve this. 114 equals Q plus 135. And it turns out that Q is, what would that be? Negative 21 joules. Okay, so 21 joules is removed from the gas. And that's the next question. Energy has been removed from the refrigerant by heat. And that's how, that's part of the process of how a refrigerator actually pulls heat out of that freezer and refrigerator compartment. All right, we'll talk about this stuff more in class. Come to me with questions. This is just part 1 of this information about the first law of thermodynamics.